The idea of a vector being in the span of a set of vectors is really quite important and essential in linear algebra because it tells us whether we can geometrically, say in this example, can we use these two modes of transportation, or vectors if you will, to arrive at the tip of the vector 3, 5. And what this means in a lot of applications is if these are the coefficients of our unknowns or variables, is it possible to create the pair 3, 5 out of them? So I've kind of said two different things here, and I want to elaborate a little bit more. So if I look at the vectors 1, 0, so 1, 0 will be a vector that points from the origin to the point 1, 0, and then 0, 10 will be a vector that points to the point 0, 10. So that's this vector right here. So there's 0, 10. Here is 1, 0. And if I can scale these vectors and add them together, which means put them together tip to tail, is it possible to get to the point 3, 5? So I'll locate 3, 5. I'll put a couple more tick marks here. So 3, 5, 1, 2, 3, 4, 5 will be over here. Now, for the moment, I'm not going to draw the vector that goes from the origin, but we'll keep in mind that is actually a representation of a vector. But like I said, I'm going to not put that there to avoid the visual confusion. So the question is, can I scale these two vectors and put them together tip to tail to arrive at this location? Well, certainly you can agree that I can take the 1, 0 vector and multiply it up by a factor of 3 to be directly below the point of interest. And now I can only take multiples of 0, 10 from there. Well, I want to get to a height of 5. So if I take half of this vector, which would be 0, 5, and I add those together, I see that 3, 0 plus 0, 5 does indeed give me the vector 3, 5 as desired. So this first vector is really 3 times 1, 0, and the reason I write it like that is because I want to write it as a multiple of this vector. 0, 5 is really 1/2 of the vector 0, 10, which again I want to write as a multiple of that vector right there. And when I add them together, I get the vector 3, 5. So the question is, how would I determine that coefficient and that coefficient right there? Well, in asking this question, we're precisely wondering whether there exists some scalar multiple of 1, 0. And I'm going to write it like this for the time being, and I'll put those values in just a moment. I'm going to write it as, this is the vector that we'll call x1, and we'll refer to this vector as the vector x2. So what I'm wondering is that, are there values c1 and c2, and those are going to be real numbers. So are there real numbers c1 and c2 such that c1 times x1, so some multiple of x1, which we already know c1 is 3, plus some multiple of x2, such that I get this vector here. I'm going to refer to this vector as b for the time being. So putting everything in place, I'm really wondering, is there some multiple of the 1, 0 vector plus some other multiple of the 0, 10 vector so that I arrive at 3, 5? Well, this is precisely a system of linear equations. If I scale the first vector and add them together, I get 1c1 plus 0c2 equals 3, and 0c1 plus 10c2 equals 5. Now I can use Gaussian elimination, I can use technology now to solve this system, but I do see that the first equation already tells me that c1 has to equal 3, and the second equation tells me that 10c2 has to equal 5. And hey, that's simple enough to solve for c2. I get, divide both sides by 10, I get c2 equals 5 over 10, which is the same thing as 1/2. So I get that c1, c2, the pair of values there is going to be 3 1/2. I was able to do it intuitively over here, but here I've set up a more mechanistic process for when things are not so obvious. Case in point, here's our second example, which involves 3 vectors in 3 dimensions. So I'll go ahead and just plot out 3-dimensional space. So here are my 3 axes, my x, my y, and my z. And I'm going to think about this as the corner of a room where 2 walls meet. So we're going to think about this as being one wall, and then we have a second wall, and here's where those 2 walls meet, is the z-axis. So the vector 2, 0, 1 is 2 units in the x direction, 1, 2, 0 units in the left or right movement, and then 1 unit up. So 1 unit up will be right about there, because remember, the perspective is, it's a little closer to us now. And so that's going to be that vector right there. Okay, that's the 2, 0, 1 vector. The 3, 1, 0 vector will just be 3 units this way, but then 1 unit this way. So it'll kind of put me right there. And then 0 units up or down. So that's basically going to rest in the x, y plane. Okay, so that's sitting on that vector is sitting on the floor. This vector is in the x, z plane. This right here, the floor, if I draw this out, so it's kind of like we're looking into a cube that has no face or no side and no top. And this right here is the 3, 1, 0 vector. 0, 0, 2 vector just points straight up 2 units like this. That is 0, 0, 2. Maybe what I'll do to contrast the colors a little bit, here is the 3, 1, 0 vector, here's the 2, 0, 1 vector, and here is the 0, 0, 2 vector. So the question is, can I scale these and put them together tip to tail, i.e. add those scaled vectors together, and arrive at the location 1, 1, 4. So 1, 1, 4 will be 1 unit in the x direction, 1 unit in the y direction. So imagine that point right there is the shadow of the point being casted down, but it's 4 units up. So it'll be, because that's closer to us, it'll be like that point right there. So can I get to that point with these 3 vectors? And the answer is not evident, because I can't figure out what scalars I would have to apply, and I can't visualize exactly how these would need to be put together. But what I'm going to do once again is call these x1, x2, and x3 vectors. And I'm wondering, are there 3 scalars that I could apply distinctly to these 3 vectors, so 3 real numbers, such that when I scale the first vector and I add that to a scaled version of the second vector, and I add that to the scaled version of the third vector, that allows me to arrive at this vector that we're going to call b. Okay, so same type of reasoning that we have here. Here it was a little bit easier to visualize, but the idea is the same. I'm going to take a vector, I'm going to either stretch it or shrink it, then I'm going to take the other vector, stretch it or shrink it, put them together tip to tail, and see where that lands me. Alright, let's replace what we know in here with what we have. So x1 is the vector 2, 0, 1, x2 is the vector 3, 1, 0, x3 is the vector 0, 0, 2, and I want to land at the point 1, 1, 4. Okay, we've already said 1, 1, 4 is right about there. And so once again, we can set up a system of equations here. We get, in the top row, we get 2 times c1. And I'll go ahead and scale these vectors first so it's a little bit easier to see. And then I'll get 0c1 and 1c1. So it's still in vector form. Here I'll get 3c2, 1c2, 0c2. Here I'll get 0c3, 0c3, 2c3. And that produces the vector 1, 1, 4. Okay, now I can write a system of linear equations here. I can just really remove all the brackets, or all the parentheses, and this says that 2c1 plus 3c2 plus 0c3 equals 1. Now I can't visualize what that solution will look like, although in the second row I see that c2 is equal to 1. c2 has to be equal to 1 because notice that this component, and this component, the y component in all three vectors, in two of the three vectors is 0. So to be able to get to the 1 coordinate in the y position that I desire, I am going to have to take 1 times that second vector to ensure that I get 1 as my component for the output vector. But I'm going to go ahead and set this up so that I don't have to manually do any work here. So 2, 3, 0, 1 will be the first row of coefficients. These are C1, C2, and C3 coefficients and our constants. And then down here I'll get 0, 1, 0, 1, or 0C1, 1C2, 0C3 equals 1. And here I'll have 1, 0, 2, 4. Okay, now I can use technology to eliminate these coefficients, and what I will get if I plug this into a matrix calculator, and we get 1, 0, 0, negative 1, 0, 1, 0, 1, 0, 0, 1, 2.5. Now, if I do just a quick check to see how many solutions is the system going to have, first of all, I see a leading 1 in every single row, meaning if I start from the left, boom, I bump into a 1 in the first row. Start in the second row, I bump into a 1 here. In the third row, I bump into a 1 here. So I know at this point that I'm not going to have 0 solutions because I can't end up with one of the equations being 0 equals 1. Because I do have a coefficient of 1 in front of at least one of the three variables in each of the three equations. I know it's not going to have infinitely many because I do not see a row with more than one non-zero value. Here I have 1, but then I have 0, 0. Here I have 0, and then a 1, but then a 0. Here I have a 0, 0, and then a 1. So I have exactly one non-zero coefficient in all three rows. I'm not talking about the constants. Those are not coefficients. In the first row, I see that it says 1c1 plus 0c2 plus 0c3 equals negative 1, which means c1 is negative 1. Similarly, in the second row, it tells me c2 equals positive 1. And in the third row, I see c3 equals 2.5, which is the same thing as 5/2. So as long as I scale the first vector by negative 1, so I make it point in exactly the opposite direction, which we can think about as pointing back this way. And then I scale 3, 1, 0 by a factor of 1. And then I scale 0, 0, 2 by a factor of 2.5. And the way you can think about that is, what do I have to multiply 2 by in order to then subtract 1, because remember c1 is negative 1, so negative 1 plus 2c3 has to equal 4, which means 2c3 has to equal 5, which means c3 has to equal 2.5. So if we plug these values in for c1, c2, and c3 and then combine these three vectors, we should get exactly 1, 1, 4. So this allows us to now understand how to figure out whether a vector is in the span of a set of other vectors, and the process still amounts to solving a system of equations. But notice the concept here is asking us, can we arrive at a specific point by taking a combination, specifically a linear combination of the vectors that we're given? And that's what it means to determine whether a vector is in the span.